All right, I think we're just about ready, you guys. See some people already have questions, so give me a minute just to get situated. Let's see. Adjusting my window. Give me a minute. All right. How to tell if an equation is endothermic or exothermic? Okay, so let's start answering some of these questions that you guys have, and I'll try to answer them the best of my ability, kind of looking at what we have here. So, first thing Molly says is asking, how can you tell if an equation is endothermic or exothermic in regards to whether the heat is a reactant or a product in a system? Let me see. I'm not 100% sure what part you want me to cover about that, but let me see what I can do. So we have two types of reaction. We have exothermic and we have endothermic. Exothermic, what this means right here is that heat is released. For endothermic, this means heat is absorbed. If heat's released, this means that heat is a product. If heat is absorbed, this means heat is a reactant. And another one that we can think about is delta H. So if it's exothermic, delta H is negative. If it's endothermic, delta H is positive. So you can think of this negative as being heat is leaving the system, so it's being released, so it's losing it, which is negative. Heat's being absorbed, so delta H is positive. So those are your differences between exothermic and endothermic. I'm not quite sure if that answers your question, but that's how you would tell. Number 5 on the equilibrium problems worksheet. Number 5 on the equilibriums problem worksheet. Let me bring that up. Equilibrium problems worksheet number 5. Okay. Let's look at number 5. So this is from a homework sheet. Number 5, we're considered this reaction. So I'm going to write down this reaction. We have 2NO. It's a gas. It's an equilibrium. We're told that it produces nitrogen gas and oxygen. Okay, so the question says the initial concentration of NO2 is 0.2 molar. What are the concentrations of all the substances in equilibrium? Okay, so let's take a look at this. So we're gonna need to create an ice table. So let's go ahead and create our ice table. So we're gonna use this reaction. I'm just gonna go ahead and put my ice on the side. And let's start filling this in. So the only thing that we're given is the initial concentration of NO, and we are told that that is 0.200 molar. If we start off with only that, and we're not getting anything else, we assume that these initially are 0. We don't know what the change is, but since it's 2, we're going to say this is minus 2x. The reaction is proceeding forward. This is going to be plus x. And this is going to be plus x. And of course, this is only x because there's no 2 out in front. Now, our change, or excuse me, at equilibrium, we're going to have 0.200 molar minus 2x. And then we're going to have x, and we're going to have x. So what we need to do is we need to solve for our KEQ, which we are given KEQ. So if I were to write out my equation, it's going to be KEQ is going to equal my products, which is N2, just raised to the first power because there is a 1 in front of there, over times O2 divided by the concentration of nitrogen monoxide squared. So when we plug this in, we're given some stuff. So we know that our KEQ is 2,400. And then we're given X times X. And then we are told that this is 0.200 molar minus 2X. And this is squared. So don't forget that squared. That's a huge thing because now what we can do, because that's squared and this is pretty much squared, is we could take the square roots of both sides. And when we do that, that gets rid of one of these x's and this gets rid of the square, which is really nice because that makes it a non-quadratic equation. So if we take the square root of this, what we end up getting is we get 48.99. This is going to equal x over 0.200 molar minus 2x. Multiply both sides by the bottom. What I end up getting once I multiply both sides by the bottom, so again, moving this over, is I'm going to get 9.798 minus 97.98x, and this is going to equal x. And what I end up getting is I get x equals 0.1 molar. So now I'm going to plug that back in. So what I end up getting for this is I get my concentrations of N2 and O2 are the same. These are equal to each other. Let's put a little equal sign. And so these are just 0.100 molar. And then my concentration of nitrogen monoxide is going to be 0.2 minus 2 times that. So this actually ends up being 0 because 2 times that minus that is going to be 0. So that is my answer for number 5. And on the equilibrium constant, let's see, we have 2A on the equilibrium constant worksheet. Okay, so this was a homework problem. Let's look at our next one, 2A on the equilibrium constant worksheet. All right, let's look at that. Oops. Okay, so we are given a reaction and we are told that we want to write the equilibrium constant expression. We want to find the value and then we want to determine if it's reactant or product favored. So let's, I'm going to start by writing out what the equation is that they give us. So if we are given this, we want to write out our equilibrium constant expression. So KEQ is going to be equal to our products, which is going to be ammonia squared divided by nitrogen times hydrogen cubed. And we're given some values, so we're going to go ahead and plug those values in now to solve for KEQ. So now we have KEQ, and we are told that the concentration of ammonia is 0.01. I'm going to add an extra decimal just so we get 2 decimals because I really don't like that that's only 1. And that's going to be squared divided by nitrogen, which we're told is 1.50. And then hydrogen, which is 2.00 molar. And then, of course, don't forget this is cubed. What we end up getting is that we end up getting KEQ equals 8.3 times 10 to the negative 6. So what this value tells us is that since KEQ is less than 1, that means that this is really big, the denominator is really big, and our denominator represents our reactants. So this tells us that the equation at equilibrium is reactant favored. So the reaction is reactant favored. So there is 2A. Go over Le Chatelier's principle quickly. Can you ask a specific question about Le Chatelier's principle? Because Le Chatelier's principle was a whole like 45-minute lesson that we did. So I am not going to review the whole thing because there's a lot of little pieces. So if you have a specific question about it, let's address a specific question. Yes, station number 7. Let's look at station number 7. Just trying to find my original copy of that. Here it is. Okay, so station number 7. So station number 7 is a little bit different than some of the problems that we saw in class because what we're told is we are looking at things and we're looking at Le Chatelier's principle in terms of colors of the reaction. So by the way that the colors change, we can tell whether or not the reaction is product favored or reactant favored. So if you guys want to look at station number 7, I'm just gonna walk you guys through this because there isn't really any math or anything to show like that. So again, we're looking at station number 7, Le Chatelier's demonstrations. So in the first one, we are told that a reaction can turn from yellow and it can go back and forth and it could turn to orange. So these are the color change that we're observing, and it gives you a reaction up top. It says, what color shift would you observe when a solution of concentrated sodium hydroxide is added? And then what you want to think of is that sodium hydroxide removes hydrogen ions from the system. Well, if you look at the reaction, what you see is hydrogen ions are actually a reactant. So if we remove hydrogen ions, what our solution wants to do is it wants to increase the concentration of hydrogen ions, which means that our reaction is going to shift forward. Since we remove this, it's going to want to increase the concentration of this because we want to undo this stress. So we have too little hydrogen ions, so we want to produce more. So our color shift would be yellow. So it's going to shift towards yellow, towards the hydrogen ions. Then we're given another reaction, and we have amber. And it goes back and forth, and it could also be colorless. So it says when this equilibrium system is placed in a cold, dry ice acetone bath. So what we're doing is that we're decreasing the temperature. So we're going to have temperature is decreased. The color disappears. Is this reaction endothermic or exothermic? So when we increase the temperature, the reaction moves in the forward direction. Well, when we decrease the temperature, what the reaction is going to want to do is that it wants to favor the side that's going to produce temperature or is going to produce heat. So if we know it's moving in the forward direction and we know that it's going to want to produce heat, that means that heat must be a product by this reasoning. So if heat is a product, that means that this reaction is exothermic. And then we have our last one on number 7. We are given that a reaction can go from pink and it goes back and forth and it will turn blue. So the first one says a solution of silver nitrate is added to this equilibrium. What is the stress? Silver nitrate removes chlorine from the system. So if it removes chlorine from the system, the stress is that there's not enough chlorine in the system. So there's not enough chloride ions. What color shift would you observe? Well, where there's not enough chloride ions, chloride is a product. So we have chloride over here. Chloride is a reactant. So if we decrease the concentration of chloride, that means that the reaction is going to shift towards the chloride ion. So when we shift our reaction towards the chloride ion, that means that our solution is going to go from blue to pink, or is going to turn more pink depending on what the reaction originally is. Lastly, this same reaction, it says that it's put into a hot water bath. So we have pretty much temperature is increased, and it says the temperature turns blue. So that means that when we increase the temperature, the reaction moves towards the products. Well, if we increase temperature, the reaction's gonna the reaction's gonna want to shift to decrease the temperature. So the heat's not on this side. What that means is that heat is on this side, because we want to move away from the heat. Because when we put it in a hot water bath, all of a sudden we have too much heat. So we want to get rid of that heat. So it's saying that it's shifting this way. So that means that heat, therefore, is a reactant. And this is also, you could also say, this isn't asking it, but you could also say that this is an endothermic reaction. So that's the Shapley's principle with some examples that apply to some color changes. Okay. Going back up. I'm a little confused about determining whether a reaction is product or reactant favored. Can you give me an example? Or are you just talking about looking at KEQ? Because there's a couple different ways. So if we want to know if a reactant is product favored, we want to look at our KEQ. And if it's product favored, that means that our KEQ is going to be greater than 1. If it's reactant favored, that means our KEQ is less than 1. And if you think about that, remember our KEQ is equal to our products. Let me erase that. KEQ is equal to our products over reactants. So notice that if our products, the concentration of our products is really high, KEQ is going to be greater than 1. So it's going to be product favored. If our reactants are really high, that means that KEQ is going to be less than 1. So it's going to be reactant favored. So based off the value of KEQ, we'll be able to tell if the reaction is product or reactant favored. On station number 2, I really can't look at station number 2. I think if you guys want me to go over station number 2, you guys should come into class for a tutorial tomorrow, because I can't project station number 2 onto the board. I really can't explain it without having the equation on there. So why don't you come in and I can review that. On the first question, third KEQ, why is it OH instead of third? Okay. Are you first review question? Did I not put the square root? It should have a square root. Maybe I just didn't put the square root on there. Let me go to my answer key. Nope, there should be a square root up there. So put it to the square root. All right. Okay, Logan, if you're comparing KEQ and Q, what you want to do, so say that you're given KEQ and you're comparing it to Q. So you calculate Q, and again, Q is the reaction quotient. So that's at any point in time. So we can either have Q being less than KEQ, and let me not confuse you guys. Let me make this a capital Q. So we can either have this, or we can have Q is this. If KEQ is equal to 1, that means that it's neither product or reactant favored. That just means that it's doesn't really favor either side. It's right down the middle. So if Q is less than KEQ, what that means is that we need to make this bigger. So that means that the reaction is going to move towards the product. So it's going to move in the forward direction. So what that means is Q is really small, and if we want to make Q bigger to go to equilibrium, we need to make it larger, and the only way to make it larger is to favor the products. Where over here, if Q is greater, that means that products is too large and we need to move in the reverse. So comparing your reaction quotient to your equilibrium constant, it just tells you whether or not the reaction will proceed in the forward or reverse. Station number 8. The first line, why is KCl going up and O2 going down? Well, if you're adding carbon chloride, it's going to go up, but the reaction is going to shift in the forward direction, which means that oxygen is going to go down. So when we look at a reaction like that, and we're looking at Le Chatelier's principle, let me bring this reaction up. So let me find this really fast. I am missing a page of my review. Give me 1 second, you guys. For some reason, I am missing a page. But what you want to think about is you have CCl4 and you have some oxygen, and I don't have the reaction in front of me because I'm missing a page, so I just have my answer key. And we're producing COCl2 and chlorine. So this is my reaction. And so what we're doing is that we're adding carbon chloride. Well, the stress is that now we have too much carbon chloride. So what's going to happen is that this concentration is going to increase. Now, to try to bring this back down to equilibrium, oxygen, we're going to favor the forward direction, and oxygen is going to decrease, which means that these two are going to increase. Now, this idea kind of confused some people, and I went over it in 6th period in a little bit more detail because some people were confused on how come if it shifts in the forward direction, how come this increases and this decreases? Why don't they both decrease? And so I said, well, let's think about this by adding some numbers. So let's say that we start off and we have 1 molar of each of these. So we have 1 molar, 1 molar, and these are just some rough numbers, 1 molar. And so this is at equilibrium. Let's say that we add some of our carbon tetrachloride. So let's say that we add 1 molar, so we get 2.00 molars. Well, we want to even this out. So we want to even this out. Now, this isn't going to go back down to 1. This is probably going to end up going, in order to reach back down to equilibrium, this might go down to 1.50. We're going to decrease this by probably 0.50, and we're going to increase these by 1.50 and 1.50, and these again are molar. So notice that I kind of shift the relative amounts of carbon tetrachloride and oxygen, but because I added 2 molar of this to get back to equilibrium, this is still higher. This is still more than my original amount. This is now less. These two are more, and these two are more. So I still have more of this because it's not going to go totally back to the 1 molar. Only some of it's going to get used up. This is what the reaction does to reestablish equilibrium. So at equilibrium, these are going to be their relative values. Now, again, I just made these values up off top of my head, but they're not going to equally distribute themselves out like what you saw before. So it is going to be slightly different, and the numbers are going to be slightly skewed. So if we look at this, and again, I don't know what these numbers are off the top of my head, but if you were to calculate your KEQ before and after, they should be the same. Which these numbers are going to be slightly different just the way that they are. But you should have relatively the same KEQ, but this is still going to be higher even after equilibrium is reestablished. All right, so go ahead, look through your notes, see what other questions you guys want to ask. Oh, there it is. Any other questions? Number 4 on the quiz. Let me see. Number 4 on the quiz. Oh. I put 2 significant figures. Oh, you want to know why? Oh, okay. I put 2 significant figures because if you look at the table, the original amount of hydrofluoric acid is 1.0 molar, but then what I'm looking at right now is that the concentration in the word problem is 1.00 molar. So you should really go off of those values, but they're different, so that's not good. So actually, if you put 3 significant figures in your answer, if you guys want to give me your quiz back, I will change that because really you would go off of that value. Your KEQ, your equilibrium constant value, you're going to assume is an exact number. So that has infinite number of significant figures, so that shouldn't limit you. But you should look at your molarities. But that's a little bit misleading again because a problem has 2 different significant figures. So if you wrote 3, if you want to bring your quiz back to me, I will give you back. I think I marked off like half a point or a point depending on how you rounded. So I will give you back those points. KEQ and KC are the same thing. KEQ is just the equilibrium constant. C just represents the concentration, but they are kind of used interchangeably. Station number 6 on the review. Okay. Yes. Let's look at station number 6. All right. Station number 6. All right. So let's write out our reaction in our ice table. So we have ammonia. We are told this is a gas. Oh, it's aqueous. Whoops, sorry. Okay, so that's aqueous. We have water, which is liquid. We're in equilibrium and we're producing ammonia, which is aqueous, and hydroxide, which is aqueous. Okay. And then, of course, we have ICE. All right. So in this problem, we are told that we have the concentration. What is the concentration of hydroxide in a 0.1 molar solution of ammonia when it reaches equilibrium? So we are told that this concentration is 0.100 molar. Now, remember, liquids don't go in our equations, so that's why those are canceled out. So if we want to fill in the rest of this actually makes it kind of easy because these are all 1 to 1 to 1. So this is going to be minus x. These are 0. We're told that there's nothing about those. This is going to be plus x plus x. So at equilibrium, it's going to be 0.100 molar minus x, and this is going to be x, and this is going to be x. Now, what is nice about this problem is that we are told our KEQ is 1.8 times 10 to the negative fifth. It's really small. So if we divide this by our initial concentration, we see that this is less than 10 to the negative 3. That's a really important idea because that's going to make our equilibrium equation a lot easier. So when we look at this and we write out our equation, KEQ, actually, let me erase that. Let me do it this way. So let's say we have 1.8. So I'm just plugging things into my equation right away. Is going to equal x times x divided by 0.100 molar minus x. Because this is less than 10 to the negative 3, we can cancel out this x, which is actually going to save us a little bit of work. It's not a huge amount of work in this problem, but it saves us from having to do a quadratic. So if we start to solve this, what we see is that we multiply this over. So this ends up being 1.8 times 10 to the negative 6, and this is going to equal x squared. And so what we're going to get is x equals, what does it equal? X equals 1.3 times 10 to the negative third. 2 sig figs, 3 sig figs. Oh, we should have 3 significant figures. So these have 3 significant figures. Let me double check my original problem. I think we need one more significant figure in this problem. Yep. Okay, let's get one more significant figure in this problem. Let's see. So if I have 1.8, hold on one second. 1.8 times 10 to the negative fifth. And we're going to take the square root of that. Oh, wrong one. Sorry, you guys. 1.8 times 10 to the negative 6 square root. 1.34. So let's add a 4 here. Again, I'm not going off this. These are exact numbers. So I'm going to go off these values right here. So there's 3 significant figures there. So I should have 3 significant figures in my answer. So that means that the concentration of ammonia, and which equals the concentration of hydroxide, is 1.34 times 10 to the negative third molar. And actually the problem only asked about the concentration of hydroxide, so that would be my answer for that problem. So that's station number 6. Can you go over the weak to strong acids in order in station number 3? All right. So when you're looking at station number 3, and I'm just going to talk you guys through station number 3 because there's not too much to show for this one. You want to look at the KEQ. When you look at the equations, what you see is that a strong acid means that it dissociates more. The more dissociation you have, the stronger the acid it is. So notice that the dissociation occurs in the forward reaction. So the more the forward reaction is favored, the stronger the acid it is. We can tell which one has a more favored forward reaction by looking at our equilibrium constants. The higher the equilibrium constant, the more the forward reaction is favored, which means that the more dissociation will occur, which means that the stronger acid it is. So when you look at those values, the weakest acid is the one that has the smallest KEQ, which would be hydrocyanic acid. That's 6.2 times 10 to the negative 10th, which means that at equilibrium, the products aren't favored that much at all. There's going to be mostly reactants at equilibrium. Next one, we see that hypochlorous acid is the next highest or the next lowest one. Then we look at our other two, and we see that our next one would be, let's see, lactic acid and then nitrous acid. Is that what I put? Can't remember what I put down. Station number 3. Yep, lactic acid and then nitrous acid, because nitrous acid has the largest value, so that means that the products are favored more, which means that more dissociation will occur. More dissociation that occurs means that the stronger the acid it is. So you want to be thinking about what is the definition of a strong acid? How does that relate to your KEQ value? All right. Other questions, you guys? Do number 9 on what? There are many different number 9s I could look at. Oh, number 9 on the review station. All of them? Because there are many, there's 4 different multiple choice. And again, these will be a little bit hard to talk about. I can kind of walk you guys through these, but because I can't project them, it's going to be a little bit more challenging to go over. 34. Yeah, let's look at 34. Okay. 34 is a good one, and this is one that was some people had questions on in the problem. Hold on, wait. Jordan 34, all but the top left. Okay. Let's look at number 34 first. So we are given a reaction 2NO gas plus chlorine gas goes back and forth, and it produces 2NOCl. And we're told that our delta H, this is a key thing that you guys want to remember, we've talked about this before, is that you want to remember what a negative delta H represents. What that negative delta H represents is that this is an exothermic reaction, which means that heat is a product. So we could rewrite this as saying 78.38 kilojoules. So we could also write it right here and showing it as a product. So we want to know what conditions of temperature and pressure will produce the highest yield of this. So we want a really high concentration of this. So what are we going to need to do to increase the concentration of our forward reaction? So we want to favor the forward reaction. Well, the first thing, if we want to talk about pressure, is that we know that there's 3 moles of gas on this side, and there are 2 moles of gas on this side. So if we want to favor the forward reaction, we need to have a high pressure. So high pressure, which equals not enough space, is going to favor the side with fewer molecules. Not enough space, and it's going to favor the forward reaction because it has fewer molecules. Now, when we look at the heat, we want to favor the forward reaction. So we want something that's going to produce more heat. Well, the way to produce more heat, if it's a product, means that if we have lower temperatures are going to favor the side with more heat. So it produces more heat. So it's going to favor the forward reaction. So high pressure, low temperature, the correct answer is C. That's how you would favor more of the product. Let's look at number 32. 32 is kind of a similar problem, but what you want to notice, and there's kind of one little trick with this one, is that we have H2 gas plus iodine solid, and we produce 2HI gas. And this is really important because what we see is this is a solid. So what we see is that this is 1 mole of gas compared to 2 moles of gas. This is going to be coming into play when we look at the pressure. We're also told that delta H is a positive 51.8 kilojoules. That tells us that this reaction is endothermic, which means that really heat's over here. So heat is a reactant. So we want to know which would increase the equilibrium quantity of HI. So what we're looking at is how are we going to favor the forward reaction? So we want to know how are we going to favor the forward reaction in this problem? Can we increase the pressure? If we increase the pressure, we're going to favor the side with fewer molecules. So the products have more moles of gas, so it's not going to favor the forward reaction. That's actually going to decrease the forward reaction. So increasing pressure is not going to do the trick. Number 2, increasing temperature. All right, if we increase temperature, we're going to favor the side that has that is the opposite of the heat. So if heat's over here and we're increasing the concentration or the amount of heat, we're going to favor the forward reaction to get rid of that heat because we have too much heat. So yes, that is going to be the right answer, where increasing temperature is actually going to favor the forward reaction, which is going to increase the concentration of hydroiodic acid. So the correct answer for that one is B, 2 only. Is that what I put? Can't remember if I put that as the correct answer. Yep, B. Number 2 only. Okay, let's look at number 3. What is the equilibrium constant expression for this system? Okay, again, so if we're looking at this system above, solid isn't going to be in the equation. So we're going to have our KEQ is going to be our products, which is our HI, and that's going to be squared, divided by our hydrogen gas, which does not have an exponent. So the correct answer is D. Our equilibrium constant is going to be hydroiodic acid squared divided by hydrogen gas. So those are those ones. You want to be very careful at looking at those subscripts to figure out if it's a solid or a liquid. Solid and liquids don't play a key role in a lot of what we're doing in these problems, so you want to be careful with those. All right. Other questions? I'm a little disappointed that some of you guys are disliking this video. Really? Really? I got thumbs down on this video already. You guys don't even know. I wish, Logan. Trust me, I wish I could say I would, but no. I mean, it wouldn't hurt to bring me coffee. It might put me in a better mood when I grade them, but that's not going to, and that might increase your grade, but it's not going to be a definite A. Erase your apple. All right. Any other questions? Any other problems that you guys want me to talk about? Logan's really trying to get his grade up. It's not even low, but he's really trying to get that A, huh? So to review for the test, I would say that you be comfortable writing your KEQ expressions. Be comfortable using your ice tables. Know the shortcut for that 10 to the negative 3. If it's less than 10 to the negative 3, cancel out that bottom X. Remember your shortcuts for if you can cancel out the square root. So if you have a square on the top and then a square at the bottom, square root the whole thing to get rid of that. Know how to compare KEQ to Q, know what to put in your ICE table or your KEQ expression and what not. For example, liquids and solids do not go into your ICE table. You want to know what your KEQ expression represents, if it's less than 1, if it's greater than 1, things like that. You have 4 homework assignments? I believe there's only, oh, there are 4. Yeah, because I split one of them into 2. Yeah, so you should have 1 homework assignment that is equilibrium constant. Then you'll have 1 homework assignment that's labeled equilibrium problems 1 through 5, and you'll have the second homework assignment, which is 6 through 10, because I split that into 2 different sets. And then you'll have your Le Chatelier's principle. If Q is equal to 1, if Q is equal to 1, that doesn't necessarily mean it's at equilibrium. If Q is equal to KEQ, so you want to compare Q not to itself. So when you're looking at Q, if KEQ is equal to Q, then you know it's at equilibrium. So the only way that you could do this comparison is if you're given one or the other. So maybe you're given KEQ and you had to solve for Q. But Q equal to 1 does not tell you necessarily if it's at equilibrium or not. All right. But you definitely want to be reviewing your homework, know some of those problems, review your quiz, review the stations. I think this is a pretty straightforward test. I hate to say that I think it's one of the easier tests because I don't think any of the tests are super hard, but I feel like it's a very good test, and based off of a lot of your guys' quiz scores from the quiz that we had, I think a lot of you guys will do fairly well on the quiz or on the test. So study, review, come to tutorial tomorrow morning. I will be there bright and early, so feel free to come by and answer questions. Also, if you want me to discuss that graph, come in tomorrow too, so I can have the graph in front of me, and I can review that graph with you. So any other questions before I sign off? Hurry up, Ethan, what do you want? You're late to the game. Station number 4. Did I do that one already? No, I didn't. Okay, let's look at station number 4. Oh, no, I didn't put it in there because most of you guys, I thought you guys knew how to find it. Sorry. Okay, I will go over station number 4. All right, here's our equation. We have 2 SO2 as a gas. Back and forth. Oh, no. Whoops. Sorry. Plus oxygen as a gas. Back and forth. Oh my gosh, you guys stop fighting in the chat. You guys are horrible. All right. So we have this. Let's create our ICE table and let's fill in the data for this. You know it. You guys are crazy. Okay, so we are told that 2 moles of SO3 is placed in a 0.5 liter container. It is found that 0.05 moles of oxygen in the container are at equilibrium filling ice. Okay, so the first thing you want to do is you want to calculate your initial volumes. Do not put moles into the ICE table. You must have molarity. Molarity is moles divided by liters. So if they're giving you moles in liters, you need to divide. So SO3, we are told, is 0.200 moles. And we are told that we have a 0.500 liter container, which means that 0.400 molar concentration of this. So this is going to be 0.400 molar. Now notice that we have only product at equilibrium. These are initially. The reaction is going to go backwards. So just keep that in mind. Then we're told that the reaction has 0.05 moles of oxygen. So at equilibrium, we have 0.050 moles, 0.500 liters. So we have 0.100 molar oxygen at equilibrium. So we have 0.100 molar. Okay, so once we get to this point, this is what you want to think about, is a reaction is going this way. Now, in order to get from 0 to 0.1, we obviously had to add 0.100 molars. So 1 mole of oxygen added 0.1 molar of this. 2 moles at SO2 are going to add double that amount, 0.200 molar of that. So we're going to have 0.200 molar. Now over here, this is not going to increase. This is going to decrease. So we added over here. We're going to take away over here 2 moles of this, which means that we're going to do the same thing that we did over here, except it's going to be 0.0200 molar. So at equilibrium, we're going to have 0.200 molar of our sulfur trioxide. So those are our values at equilibrium. Again, we only start out with our quote unquote product. Remember, this is kind of a weird thing. This reaction goes back and forth. We call this our product only by convention. It doesn't necessarily mean that that's our product because this reaction is going back and forth. So we start off with this, which means our reaction is going to go in the reverse. So these are going to be adding. These are going to get larger. This is going to get smaller. And so I subtract that. So now we can plug anything. Now we can plug everything into our KEQ expression. So KEQ is going to be our products, which is 0.200 molar squared, divided by our reactants, which is 0.100 molar, which is our oxygen, divided by 0.200 molar squared. And so what we end up getting is our KEQ being, what is that, 10? Yep. We get KEQ equals 10. This 10 is greater than 1, which means that our reaction is product favored. So KEQ, just kind of a side note, is greater than 1, which means it's product favored. So there's that problem. So again, review your stations. Let me know, write down your questions that you guys might have. So as you guys are reviewing your stations, as you're reviewing your homework, write down questions that you have and make a note of those questions so you guys can come ask me in class. Why am I getting another thumbs down? Really, you guys? Now I have 4 thumbs down? You guys are mean. You guys are really mean. I take that personally, you know. All right. I am going to go ahead and log off, review. I hope you guys have a good rest of your evening. And I will see you guys later. Jordan, why are you giving me 3 thumbs down? Jordan's going to get an F. Just FYI. Just kidding. All right, you guys. Have a good rest of your day or evening, and I will see probably a lot of you guys in the morning at tutorial. Study, study.